Yes, Pavan. So I welcome back Dr. Pavan Kumar from IIIT Dharwad to continue his session, thinking the previous concepts and how it is going to be useful in artificial intelligence to first order logic. Pavan,
Yeah, yeah, thank you, sir. Yeah. Once let me share the screen. Hope I'm audible, right?
yes, you are audible.
Is the screen is visible?
Yes, yes,
Yeah. Okay. I just want to continue with the previous example which I was discussing on. Like we have seen, in the negation example. See, now I have represented this example by using a variable p. You can do it by using any variable q or there is no relation. And also this also I can use it. And there's a variable which can take value. So I can represent this by using q and then negation q. So if I represent in the same example, if I'm representing this also with p and this also will p, then it will be a difficult thing. But if I can use it in two different examples, then that is fine. Like I can use it as another example. I can use the same variables p and negation p for representing the same. So just we were discussing on the negation operation, and we have seen that if an proposition is giving a like meaning, like now Bangalore is in India, it's have a truth value of 1, then the negation of that will obviously have a truth value 0, right? So similarly I took then another example wherein I took an example where Chennai is not in Tamil Nadu, but I was representing that with P. It need not be with P. You can take it in anything. So here also, like that, I'm just giving a general representation as P. Even it can be Q or something else. Okay. So this is similar to our membership table. So how many rows are there in this case? So I'm dealing with only one variable. So the number of rows in this membership table is called as like 2 power the number of variables. So only one is there. So two entries are possible for this table. But here we don't use the convention of the membership table, but here we will use it as truth table. We use the notion as truth table. Similarly, we have different truth tables. Like for example, if I take another example wherein I will take it for the conjunction or for the AND case. Like if I use the conjunction or the AND, right? Now I require two variables here. Like if there are two propositions which are indicated by P and Q and their connection by P and Q. So like if now P is having an value, that is the membership value or the truth value as 0, right? Yeah, before that, like how I fix the number of rows required over here. So two variables are involved or two propositions are involved here. So the number of rows required are 2 power 2, that is 4, right? So now, like now this, the proposition P is having a truth value 0 and Q is also having truth value 0. And this is having the truth value 0 and this is 1, 1, 0 and 1. And how would the truth value of this? So this is predefined. So if both of them are having a value 0, then P and Q will also have a value 0. When this is 0 and 1, then also it will have a truth value of 0. That is for the combined proposition. That is P and Q is also called as combined proposition. It's called as combined proposition or a complex proposition. Whereas P is called as a simple proposition. Here we are adding more than one proposition, so it is called as a complex proposition. And when the entries are 1 and 0, so P and Q is 0. Only when both are true, then this is 1. And also, like, don't get confused. Like some of the authors will even use this convention of truth and false. That is, instead of zeros and ones, they use the notion of F and T. So if it is false and false, then the value is false. So if it is false and true, then it is false. If it is true and false, then also it is false. If it is true and true, then also it is true. So we will stick to one convention of zeros and ones, so that will help us to solve certain things. Now, like if I take an example, like P is denoted like root 2 is a rational number. So root 2 is an, okay, I will take to root 2 as an is an irrational number, right? And also I will take another statement. I can take any of the variables. I will just take the S for this case. I will take 9 as a prime number. Now, if I represent this as P and S, then the statement will be root 2 is an irrational number and 9 is a prime number. How do I write it? Root 2 is a irrational number and 9 is a prime number. But what is the truth value of this compound proposition that is having, okay, it's also called as the compound proposition. Another way is like you can write it as compound proposition. So P and S is a compound proposition. What is the truth value of this? So now to understand the truth value of this, first see what is the truth value of the first statement and then the logical connectives and what is the truth value of this, right? So root 2 is an irrational number. Yes, that it is the true. So the truth value is 1. So 9 is not a prime number, so its truth value is 0. So now this will be evaluated to P and S. So it is 1 and 0. So if it is 1 and 0, that is S0. So the value of this compound proposition or the truth value of this compound proposition is 0. This is how we define the things in the case of the conjunction. Next, moving further, we have something called as disjunction, that is the OR. So we will first see how will be the truth table of this, and we will take an example and we will see it. I will take the two variables for this one where they are indicating two propositions P and Q. What are the possibilities that this can be, both of them can be false, or one of them can be false, and then both of them can be true. In this case, the truth value is given by P or Q is there, then either of them will be taken, which is a high. So if you are from a digital electronics background, then also you can connect it to the digital logic. Now this disjunction is like something called as an OR gate. Okay, it is represented by something like this. It will have two voltage points, that is P and Q, and this is the output. Now if the P is low and Q is low, then the output is also low in the case of an OR gate. So if the voltage is low, one of the voltage points is low and the other is high, then the voltage, the output is high. Like if you use this for signal processing also, there is the same logic will be used for the logical gates. Anyhow, that is not in the scope of this subject. So just understand that this is the same convention that is even used in the digital logic. So this is the disjunction truth table and it is having the 4 variables. So if I take the previous example, right, I was talking about root 2 is an irrational number, or now if I take this P and Q the same values, then I will write P or Q as root 2 is an irrational number or 9 is a prime number. Now, what is the truth value of this compound proposition? So, if I evaluate to the simple thing, then this is having a truth value 1 and this is having a truth value 0. So, a combined truth value of PRQ is, it is 1. Because according to this, we will take this as 1 and 0. So, it will have a truth value as 1. Right? Similarly, we have something called as exclusive disjunction. The above thing which we have discussed is just a disjunction, which is also called as an OR, which is represented by this. And exclusive disjunction is something which can be represented by two symbols, either by this or by this symbol. So now, if you are having the two propositions P or Q, then how do we define this exclusive disjunction? Okay. So how does it work is, if both of them are true or false, then their compound truth value is false. If either of them is true, then their value evaluates to 1. Okay, so if I use the same notion over here, taking the same example, I can represent this by this symbol or by this symbol. What I can see is, or if I write a statement, right? But how do we write this in the word form, right? Then this will be write this as either root 2 is an irrational number, either root 2 is an irrational number, or 9 is a prime number, or 9 is a prime number, right? See, now if I again evaluate it, so this is having a truth value 1 and this is having a truth value 0. So 1 and 0. So the value of this compound proposition is logical connective. So we have seen 3, like now conjunction, disjunction, and exclusive disjunction. Now comes the important one, that is called as the conditional. Conditional is a compound proposition obtained by two given proposition by using the words if and then. Am I getting a, like, is it the noise from my side?
Not sure, but it will stop.
Okay. Right. Like if and then is there, then in that case, like if you are given, yeah, any doubt? Okay, like if there are two propositions, if there are two propositions, P and Q, if they are connected by if and then, that means like if P, then Q, right? Or they can be if Q, then P. Both are same. So this kind of a case is indicated by the symbol P implies Q. That is if P, then Q. This is how it has been read. But more importantly, like when you're having the symbols like P and Q, it is equivalent to having Q and P. When you're having P or Q, then it is also equivalent to having Q or P. Then if you're having P exclusive or Q, it is also equivalent to having Q exclusive or P. But P implies Q is not equal to Q implies P. Just have this thing in mind. Then coming for the truth table of this conditional, like P and Q, then P implies Q. Anyways, like we are not going to into the proof of why this conditional is giving this value. So now if I write the truth table of this, so this truth table's value, the P implies Q's value is dependent on the value of the Q, right? So like how we write this truth table is, like when this is both are 0 and 0, then the truth value is 1. When both of them are true, then the truth value is also true. But in this case, like when P is false and Q is true, then the truth value is 1. And when the P is true and the Q is false, then the truth value is 0. Or in other words, what I can say is, like the truth value of the conditional P implies Q is 0 only when the truth value of P is 1 and Q is 0. In all the other cases, the truth value of P implies Q is 1. Just remember this. So this is the way this truth value is being defined. So this is 0 only when P is true and Q is false, or P is 1 or Q is 0. Then only the P implies Q is 0. In all the other cases, it is 1 itself. Or I can write it in the sentence form. The conditional P implies Q is false only when P is true and Q is false. In all other cases, it is true. Now we will take an example and see how this works, or how do we represent that. Now assume that example P. So it is a proposition which says that P2 is a prime number, and then Q is another proposition that says 3 is also a prime number. Now, what is the P implies Q value over here? Right now, if I see this is true and this is true. It is 1 implies 1. So by the membership table or the truth table, we can say that this compound proposition of P implies Q is having a truth value as 1. Okay. Now the next another thing is there that is called as biconditional. So in the case of the biconditional, if P and Q are two conditionals, or not two conditionals, if P and Q are two propositions, then the conjunction of is written by P implies Q, right? Similarly, like how the biconditional works is, if P and Q are two propositions, then the biconditional is represented as this one. Like you can say that a line with arrows on both the sides. So this is how the biconditional is written. But this biconditional is equivalent to having P implies Q and Q implies P. Just observe this notation. How this is equivalent is, this is P implies Q and Q implies P. But how do we read this? How do we read this is P if Q. It is having IFF, or P if and only if Q. Or also it is called as if P then Q, and if Q then P. It's a both way round. But how do we give the truth table for this case? So now, like, we are having the same two variables I am taking. So how many values it will have? Either this can be 0, 0, 0, 1, 1, 0, and then 1, 1. So now to understand the truth value of this, what we require, the ingredients, we require P implies Q, and then Q implies P, and then we require the conjunction of these two, that is P implies Q and Q plus P. This is also equivalent to P if and only if Q. So P implies Q from the previous truth table, we know that this is 1, this was 1, this is 0, and this is 1, because it is 0 only when P is 1 and Q is 0. In all the other cases it is 1. Similarly, in this case, it is 1, it is 0, it is 1 and 1, right? Now, if I do the conjunction of these two, then this is 1, 0, 0, and then a 1. Right? So this is quite opposite. This biconditional is quite opposite to the exclusive OR case. In the case of exclusive OR, when both the values, both the truth values are same, then the output used to be low, or it has to be false. But in this case, if both the truth values are same, that is, if both of them are 0, then the output is 1, or you can even say that the truth value evaluates to be 1. This is how the difference between the conditional and the biconditional. Then to take some example, like how do we construct the truth table if an example is given? Like now I will take an example and will show how the values will be. Now assume that P implies, like if I am asked to show that P implies Q or R is false, then how I will do this? Right? Now how I can show that this is false? And when this can be false? This can be only false when this value can be false. Like we know from the truth table that P implies Q is 0 only when P is 1 and Q is 0. So this can be false only when Q or R is taking a value 0 and P can be either 1 or whatever, right? Now this Q or R is false only when both of them are false, because we know from the truth table of R that Q or R will take a value 0 or 0. If I take 1 and 0, then the value will become 1. Then this is not possible. So this is false only when Q is false and then R is false, right? But how about the P case? So if the P is 1, when both of them are false on the right hand side, then this will become a false thing. If it becomes a 0, then it will become a truth thing. So for this to happen, P, Q, and R should take the values respectively 1, 0, and 0. Now, if I represent this 1, 0, and 0 and substitute over here, then this will be a false statement. This is how we will prove some of these problems. Now, like if I ask you to construct the truth table, now if I ask you to construct the truth table for PRQ and R, how do I construct? Now, three propositions are used because they are different, P, Q, and R. So 2 power 3 rows will be there. That means this P, Q, and R will take different values. Check like all the right. Now what I require to evaluate here is like what is P and Q, sorry, PRQ, and then PRQ. I will tell you like what is the use of doing this table at a later stage. But just understand that this is how the truth table is constructed for a given compound proposition. So PRQ is like just take the values from these two. So this is a 1, 1, 1, 1, 1 and a 1. So I will take this one and perform OR with this. This is 0, 0. This is a 1, 0, 1, 0, and then a 1. Now, this is what the value of this compound proposition is. So, when the values of P, Q, and R vary, accordingly, this will also vary to certain extent based on this values. This is how we give the value for the compound proposition. But what is the application of this? Right? So that's why, like, how do we use it in artificial intelligence? That also we will see quickly. Now, there is something called as tautology. Tautology, and then we have contradiction. These two are the concepts which are purely which we can come to a decision that something is a tautology or a contradiction by the compound propositions or in general from the logic table or the truth table which we consider. So what is tautology? A compound proposition which is true for all the possible values. That is a compound proposition. We will see an example. A compound proposition which is true for all possible truth values, for all possible truth values of its components, for all possible truth values of its components, then it is called as tautology. Hope I'm connected, right? Are you able to hear
Yes,
me?
sir. Yes,
Yes,
sir.
sir.
Yeah, because in between, if there is no noise, sometimes I get confused whether I'm
Yes, sir.
connected.
It's clear.
Yeah, okay. So now a compound proposition which is true for all the truth, a compound proposition is a compound proposition which is true for all possible values of possible truth values of its components is called as tautology. It's called tautology. I will give an example and explain what is tautology. Similarly, contradiction is this is tautology, and what exactly a contradiction is a compound proposition which is false. A compound proposition, a compound proposition which is false for all possible truth values. See, don't be confused that truth values is not the true value. Truth values in the sense that can be either a 0 or 1 of its components is called contradiction. Like, see, when a compound proposition is given, either you should evaluate to tautology or to a contradiction. But first, I will explain what is the tautology and what is the contradiction. Then we will see what is the next thing, right? Okay. Now, I will take an example and then I will come back to this. Now I will take an example wherein I will try to construct the truth table for this. P and P implies Q and implies Q. Now if I construct the truth table for this, so it will be like we are having only two propositional variables. So, and I require Q, okay, and I require P and P implies Q. Then the entire given case, that is P implies Q and Q. Now this will take the value either 0, 0, 0, 1, 1, 0, and then 1, 1. Okay, great. Now if I enter the values out here, this we know that when both of them are having a truth value like P implies Q, then this is 1. So in this case also 1. This is 0 and this is 1. Now this is P and P implies Q. So this is 0. So this is a 0 and this is a 0 and this is 0 and then this is also a, sorry, this is a 1. Right? Now if I take this value, that is this column and then this column. So this is our part, right? So now this is 0 implies 0, this is 1. This is 0 implies 1, this is 1. 0 implies 0, 1. Right. Now if I evaluate or this check this, inspect this column, particular column, all the entries in this column is 1 irrespective of its components. That is, irrespective of what the values P or Q is taking, at the end, the compound proposition evaluates to 1 in all the possible cases. So such cases wherein the compound proposition evaluates to 1 for all the possible combinations, it is called as tautology. So I can say that now this is a,
So, excuse me, sir.
yeah, right.
So the last one should be 0.
This one,
Yeah,
why?
because the previous one is 1. Like the first one is 1, and then it implies Q. So
Yeah, 1 implies 1, so it is 1. See, if you observe the truth table of P implies Q, how was the truth table? Like if it's having this one, how do we define it? Only in the case when this P is true and Q is false, it is 0. In all the other cases, it is 1. Right. So if I use that logic over here, then it will be the same. Right. That's how it's a tautology. Now, let me take another example.
Pavan,
Yes.
someone has texted me saying that if possible, try to change the color of the ink from red to something else.
Okay, color of the this one, red to something else. I don't know whether it is possible. I'll just check.
Now just right click it and you can get the ink color.
Okay, okay. Yeah, okay. So, which is favorite color? Anyone can say?
Black.
Or black? Okay. So now, like if you can observe this one, the entire entries in this column is 1, right? So it is a tautology. So similarly, we will see an example for contradiction and then we will come to the discussion why it is important. So if I take an example, like something like this, okay, for a contradiction, I will take an example. Yeah, P and negation P and Q. If I want to show it as a contradiction, then from the truth table or whatever I will arrive should have all the values to be false or it should be all zeros. So if I construct that, P, Q are required and also negation P is required, and then P and negation P and Q. And also more importantly, like how we do deal with the arithmetic operations, right? The first we will deal with something what is inside the bracket, and then we will deal with the outside. The same thing applies over here as well. Okay, so now the two variables are there. So the membership table or the logic table will have 4 entries. So this negation P is 1, 1, 0, and then 0. So P and negation P and Q. So like if I take, okay, I need another table. Okay, I will another column, negation P and Q. Right. So now negation P and Q. So if I use these two, then this is 0, this is 1, this is 0, and this is no, wait, I made a mistake. Negation P and Q. Yeah, this is 0, 1. Yeah, 0, and then 0. Yeah, I was right. Yeah. Now if I do this AND between negation P and Q and then P, so this will be 0. So again, this is a 0. This is a 0, and this is a 0. So if I observe this particular column now, all the entries in this is all 0. So whatever may be the particular values of P and Q, this will evaluate to zeros. So this is called as contradiction, right? Now you may get a case, like it is not the case always. That means sometimes you may get few ones and few zeros. In that case, that is called as contingency. That is called as contingency, wherein the output or the compound proposition evaluates to, few of them will evaluate to 0 and few of them will evaluate to 1. Such case will call as contingency. If all of them evaluates to 1, then it is called as tautology. If all of them are evaluates to 0, then it is called as contradiction. So this is a contradiction, and also it is called as absurdity. It is also called as something as absurdity. Okay, just have this name in mind, that this is also called as absurdity. So this is how the two things are defined. That is what is contradiction, tautology, and then contingency. Next comes logical equivalence. How we can say that these two are logically equivalent. So now we can see slowly that how the information, that is the statements which we were considering earlier as propositions, are converted into symbols, and we are dealing with only the symbols, right? So now we are taking, like we have seen the logical equivalence, like so we have seen how this can be a tautology, contradiction, and then a contingency. Now we will see how we can take it further and see when two compound proposition are logically equivalent. That means you are having a compound proposition U, which in turn can have many components, and another compound proposition you are having an V, which can in turn have many components, when these two can be logically equivalent. So how do we do that, right? So this is called as logical equivalence. So when we can say that two propositions U and V are said to be logically equivalent whenever you have the same truth value, whenever U and V have the same truth values. That is, like either this should be a tautology and also this should be a tautology, or this should be a contradiction, or this also should be a contradiction. When then we can say that two propositions are equivalent, or by simple, even we can say that U by conditional V is a tautology. So when we can say two propositions U and V are logically equivalent when U by conditional V is a tautology. Okay, like that means U by conditional V means it is equivalent. We have seen previously this is equivalent to U implies V and V implies U. So this should be, that means the value of this should evaluate to all ones. Then we can say that two compound propositions are logically equivalent. Okay, this is the notion. But now continuing this case, next we will see something called as laws of logic. How we can use laws of logic, and which are the laws of logics are there. So one of the prominent is this law of double negation. There is something called as law of double negation. So which says that if you are having a proposition P, then if I take the negation of the negation, right? So this is equivalent to having a P. That is the law of double negation. Then comes something called as idempotent law. These are all the concerning with the laws of the logic, that is involving the proposition. Whatever we have seen previously was just using the set theoretical concept. So in the idempotent law, it says that if you are having P or P, which is also logically equivalent to P, and if you are having P and P, this is also logically equivalent to P. Then comes the identity law, which says that P or F, that is logically equivalent to P, and P and truth, that is also logically equivalent to P. Then comes something as the inverse clause. So inverse clause says that P or negation P is there, then it is logically equivalent to truth, and then P and negation P is there, then this is logically equivalent to false. What does it mean is, like, you can analyze each of them. I won't go into the detail of these, but just understand that if you are having something as P or F, that is the proposition will take some value, and then that is ORing with F naught, that is always false. See, now this is dependent on the value of the P. Now if the P is false, then it will take value false. If it is 1, then it will take the value 1. Now if you are doing the OR of this, right, now this is 0, then obviously negation of P will be 1, and if I take OR of these two, then this will be truth. That's why it is given as. So now P is 1, suppose say, and then the negation of P will be 0, and 1 and 0 is 0, that's why we are giving it as false. So using that convention, these laws are derived. Then to continue in the same fashion, there is something called as commutative laws. For completeness, I am just introducing you the commutative law.
So
So
please explain third and fourth point.
third and fourth, yeah, okay, this one.
Yes.
See, now you are having something as P or F naught, right? So F is always false. That means the value is 0. Then P can take a value either as 0 or 1. So assume that at one stage it will take a value 0. Then 0 or 0, that will be 0, right? So this is equivalent to taking a value of P. When P was 0, the P or F naught is also 0. That was the value of P. When it was 1, then 1 or 0, then also the value is 1. So that is the value of P. So value of P is playing a major role over here. What is an identity element? So identity along element along with any element will give you the element itself. So F naught is an identity element for this P under the operation OR. Similarly, if you are having P and T naught, now this is also dependent, this value is equivalent to P. This is also dependent on the value of P, because truth is always having the value 1, right? So now if this P is having value as 0, then 0 and 1 is 0. The P is also 0 in this case. So if this is 1 and 1, then also it is taking a value 1, whereas P is 1. That means P0 is acting as an identity element in the case of the AND logical connector. Now taking this example of P or negation P. Now if P is taking a value 0, then negation P will take a value 1. If I perform the OR operation of that, then I will get a value 1. So 1, if I am getting in that case, that is always a truth value. So it is P naught. So now if I am having P and negation P, negation P. So if P is 1, then obviously negation P will be 0. And if they are connected by an AND operation, we know that 1 and 0 is always a false. So we will get the false. So you can see that. Yeah. Okay. Now, commutative property is something like this. So commutative property is logically equivalent to P or Q is equivalent to Q or P, and P and Q is logically equivalent to Q and P. Right? Then again, we have something called as De Morgan's law here, not the previous law. It is something different over here. So if you are having a negation P or Q, it is logically equivalent to having negation P and negation Q. And if I'm having negation of P and Q, then it is logically equivalent to negation P or negation Q. What I'm doing over here is the negation of P or Q will be negation P. This or will be changed to and then negation Q. Similarly, this P and Q is negation of P and Q. This will be logically equivalent to negation P. This and will be converted into or and then negation Q. Then comes the associative property, which will be like P or Q or R is there. It is logically equivalent to having. It means you can operate these two first and perform the OR with this one, or perform the operation with these two and then perform with this. Similarly, it will applicable to the logical connective and also, but not the combination of both. That means these two are valid, but it is not applicable for the case of this. That means it is not logically equivalent to having this one. Okay, just have this notion in mind. This is not logically equivalent, but these two are possible. Then comes the important one is the distributive. So distributive is like now P or Q or R, Q and R. This is logically equivalent to, like I am distributing this R over the element. That means it will be P or Q and P or R. Similarly, if I'm having P and Q or R, that will be equivalent to, I'm distributing the AND over these two elements. So this is P and Q or sorry, P and R. That means I'm distributing the elements over here. But now, what is the use of these things, right? Now, like to see that, what I will do is, like first we will take the negation of P implies Q. How? No, before that, okay, I will take another example. Now, negation of how these laws are derived, right? We know that negation of P and Q is equivalent to negation P or negation Q by De Morgan's law, which we have discussed. Now, how do we arrive at this conclusion, or how do we arrange it? By using the help of the truth table. But now this became a law or a formula to use it directly. So we will see like how this has been proved, and what we require: negation P and then negation Q, and then negation P or negation Q is there. Now, anyways, the two variables are involved in even in this case. That is, so that's why the number of rows will be there will be 4, right? So 0, 0, 0, 1, 1, 0, and then 1, 1. And how about the entries now? P and Q is 0. This is 0. This is 0 and this is 1. Negation P will be 1, 1, 0, and 0. So this will be 1, 0, 1, and 0. Now coming to this aspect, negation P or Q. So 1 by the OR operation, either this is high or this is high. This is 1, 1, and then 0, right? Okay, one more thing I require, right? The negation of P and Q. That's why, like, but there is a no count on giving how many columns will be there. It is depending on the case which we are dealing with. So if I take the negation of P and Q, this is 1, and this is 1 because negation of this, and this is 0. Now, if I observe this column and this column, they are exactly the same, right? For all the possible combination, these two columns are same. So by these two, I have arrived at this conclusion that, okay, this result is true. But now, anyhow, this is popularly called as De Morgan's law. That's how these laws are being defined. Okay. Similarly, even you can use any of the laws and you can come out with these things. But the important among all is, like, there are some conditions or which are quite important to arrive at the result. That is, like, now P implies Q is there. How to deal with this case? So that's why one of the important results, assuming this is like P implies Q is logically equivalent to negation P or Q. So that means if a conditional statement is given, that is, if I say that if P then Q, then it may be difficult for me to analyze this. Then what I will do is I will convert this into negation P or Q, and then I will solve it. But this equivalence can also be proved by using a truth table kind of a thing. That is negation P and Q I'll just quickly write on this so that it will be easy for you to understand how I write this. But I am writing it this from the memory because I'm using it for quite a long time. But even you can practice it and you can get to write it. So this is 1, this is 1, this is 0, and this is a 1. So now negation P is 1, 1, 0, and then a 0. So this, okay, this should be negation. Okay, anyway, Q is there, right? So I don't require it because Q is already there. So negation P or Q. So negation P or Q. So this is 1 and this is 1, right? So negation P or Q. So this is a 0. Negation P or a Q. Negation P or a Q. So this is 1, right? Now if I observe these two columns, they are one and the same. That's how I can write this as P implies Q is logically equivalent to negation P or Q. Similarly, even I can extend this to like taking negation on both the sides. That means negation of P implies Q is logically equivalent to negation of negation P or Q, or if I simplify this side on the right hand side, this will become negation of negation P. So negation and negation cancel out and I will left out with P, and this or will become and this will be negation Q. Even you can use a truth table to identify this and then do it. Right, now comes the important part. What is the use of knowing all those things? Right, now if I'm having a statement, suppose say if x is an integer, then x is a rational number. Now if I ask you to write the negation of this statement, how do we write the negation? We don't know because it is in conditional format. So now x is an integer. This is, if I consider this as P, and x is a rational number, if I consider this as Q, then symbolically I can represent this as P implies Q. Now if I want to do the negation of this, then I should take the negation of P implies Q. So if I do this and then write down it in the form wherein we arrived at previously, then this will give the negation of this statement. So if I write this one as x is an integer and x is not a rational number, then it is the negation of this given statement. That is, if this compound statement is given by P implies Q, then this statement represents negation of P implies Q. But what I have done is, I don't know how to directly deal with this kind of a statement when a conditional is there. So what I have made is, I have converted them by using the previous law which I have proved. That is, P implies Q is negation is equivalent to negation P or Q. So if I apply the negation, then it will become P and Q. See, if it is a simple statement, then you could have easily negated it. That is like if I say that Bangalore is in India, right? If this is one of the proposition, then if I ask you to do the negation, it is quite easy. That is, Bangalore is not in India, right? But if I give you the conditional, then it will be difficult. So if I know this truth value and also the simplification form, then it will be easy to do such kind of simplification. See, for us also it will take some time to understand, but think how exactly we can represent this to a computer, and the computer will access or do some information or processing on it. So we should represent the knowledge to the computer in such a way that the computer should be able to take a decision. So that is done by something called as rules of logic, or the rules of logic we have seen, that is called as rules of inference. Rules of inference. So inference in the sense, now you are given with a set of statements. Now what we can infer from those set of statements, right? We have seen the propositions now, like P, Q, and or all the propositions we have seen. Now assume that P1, P2, P3 and so on are all the propositions, right? And then from this proposition, we can form a compound statement that is P1, P2, P3 and so on up to Pn. This is a compound proposition because they are all the propositions are connected by an logical connective and, right? So now this kind of an proposition, if this evaluates or this will be of the form, is called as an argument. It's called an argument. Like now what I'm saying here over here is like now you are given with the propositions, they are connected by the logical connectives and if it evaluates to Q, if that evaluates to Q, that is called as an argument. So now here the P1 to Pn are called as the premises of the argument. It is called as the premises of the argument and Q is called as the conclusion of the argument. Right? Now you are given with the premises. Premises are nothing but our propositions which are connected by a logical connective and by default these premises are assumed to be true. By default premises are true, but Q we cannot say, that is Q is a conclusion that defines whether the argument is true or false. So by using these arguments, I can come to a conclusion that can be a true conclusion or a false conclusion. That means the conclusion can have a value 0 and 1. So if I am given with the premises, that is P1, P2, P3 up to Pn, like we will take an example and I will explain you again. Assume that there are propositions P1, P2, P3 up to Pn. These are called as we are putting up some kind of an argument. So what is the conclusion of that argument? It can be either true or the false. Okay. So when these are given, then we will put forward all this in this format, and from this we will derive, like this will be okay, like I will write down here clearly, P2, P3 up to Pn. These are all the statements or the premises which will argue something. Okay, from these premises I will come to a conclusion. So because of this, these are all assumed to be true and they are connected by a logical connective and. Okay, so P1, P2, P3 up to Pn. So because of all these premises, I have come to a conclusion. This conclusion can be true or a false thing. Right? To proceed further, we require some laws over here for the rules of the inference. Okay, so one of the rules is, which is called as rule of conjunctive simplification. The rule of conjunctive simplification. So the rule of conjunctive simplification says that if there are two propositions P and Q, if P and Q is true, then P is true. That is, like if P and Q are there, then you can just write from them only the P. I'll just explain you why this is. Like just remember, these are all the rules are there. Then we can argue how this is useful in artificial intelligence. Okay. Rule of, then comes the rule of disjunctive amplification. I will just write this name and then what it is. This is your Q. Then a rule of syllogism is called as rule of syllogism. What it says is, if you are having the two compound propositions P and Q Q implies R, from them I can write a conclusion saying that P implies R. Then two more important rule is, one is modus ponens, which is that if you are having the argument of the type P and P implies Q, therefore the resultant is Q. I will also say how we can use this. Then we have something called as modus tollens, which will have the argument of the type P implies Q. Two propositions are there. One is P implies Q and the other is negation Q. And we can conclude that saying it is negation P. And another rule which is called as rule of disjunctive syllogism. It is not the rule of syllogism. That is called as disjunctive syllogism, which says that if you are having the compound proposition P or Q, then negation P, therefore Q. Now we will use this set of rules of inferences. These are all the rules of inference. Okay, these are all the rules of inference, and then how we can come to a conclusion. Right? I will take an example. If Sachin hits a century, then he gets a free car. Then the second one is Sachin hits a century. So therefore, Sachin gets a free car. Now, how do I verify whether this is true or whether it is false? Right? What I will do is I will represent that symbolically first. I will assume that P indicates Sachin hits a century. Okay, and Q indicates that Sachin gets a free car. Now, if I represent this symbolically, then the first statement will translate to P implies Q, and the second just implies P. Right? If I represent this problem in the form of symbolically, it is P implies Q, then P, therefore Sachin gets a free car, so therefore Q. Right? Now the argument what I'm saying is, if Sachin hits a century, then he gets a free car, and then Sachin hits a century. Now I need to verify like whether Sachin gets a free car is a valid statement or not. What I will do over here is I will check the rules of the inference which I got here, and then I will check I have got anything similar to this. So if I observe all these rules of inferences, I can see there is a rule by name modus ponens. It says that if you are having two propositions, P implies Q and P. See, we know that AND operation or the thing is distributive. So it is equivalent to having P implies Q is equivalent to having, sorry, P and Q is equivalent to having Q and P. Now I'm having two statements, that is P implies Q and P is logically equivalent to having P implies Q and P, right? So now I'm having this. So therefore Q is a valid statement by the rule of modus ponens. Okay. So now if I give these two statements, okay, to the computer and says that, okay, I'm representing this knowledge to you, what you can conclude from this. So now I have got an argument saying that I will give this statement also to the computer. Now can you take any decision based on this, whether it is a valid result or invalid result? So whether Sachin gets a free car or not. Right? Now, if I represent these two statements to the computer, then it will process it symbolically and it will say, okay, you have given a free car to the Sachin. By the view of modus ponens, it is a valid statement. Like that, the computer will evaluate. This is the logic. That means we are using this logic to build a intelligence. So now the computer can take a decision based on this. Okay, if Sachin hits a century, then he has to get a free car. Right? So in this case, Sachin has got a free car. So by the view of the modus ponens, this is valid statement. Now assume that Sachin won't get a free car. Sachin won't get a free car. Now if I observe this case, any of the rules of inference, that will not correspond to this, right? So the resultant should be only Q. So if I get that the Sachin won't get a free car, the conclusion is negation Q. None of the rules of inference will support this. So the computer should take a decision that, okay, there is something is wrong. So based on the fact, it has to take a decision that, okay, fine, something is wrong. Let me say that it is invalid. So that is how it will take a decision whether it is valid or invalid, right? So similarly, if you take another example, like for example, you are having some statement like somewhat okay. If I drive to work, if I drive to work, then I will arrive tired. I am not tired. Another statement, I am not tired when I arrive at work. Therefore, I do not drive to work. Now I need to check whether I am talking sensibly or not. The computer should take a decision. So first I will try to represent this symbolically. Then what is P I will do is I drive to work. Similarly, Q I will take it as I arrive tired. Now only these two are required. So if I represent this symbolically, what will happen is if I drive to work, then I will arrive tired. I am not tired, so I will represent this Q. But the conclusion here is I do not drive to work. I do not drive to work. So that means the statement is P implies Q and negation Q is there. So if I observe this rules by the view of modus tollens, right? So P implies Q is there and negation Q is there. Then I can say I have arrived at a result negation P. So this is a valid statement. Now, like if I write, I do not drive to work or drive to work, right? If I write it as slightly that I drive to work, then this will become, the representation will be P implies Q, negation Q, therefore P. But none of the rules or inference supports this. So I will say that this is invalid. It is not possible. That is how the computer will rule out and take a decision. But now this is like we are talking about if I drive, if I am not driving, then I am just talking about the particular cases. How we can take a generalized decision? For that, there is something called as quantifiers. There is something called as quantifiers to represent the same. Now, suppose you have seen the declarative statement previously, which are called as propositions. But here also we can have some statements like x plus 3 is equal to 6, and then x square less than 10x divides 4, right? Now, these are all the open statements, and also these are propositions. See, based on the value that x takes, it will become a valid statement or an invalid statement, or it will have a truth value 1 or 2. Like suppose now x will take a value 3, then the truth value will become 1 in this case. If x takes a value 2, then truth value will become 0. But this is a valid statement. Similarly, this x square, now x square less than 10. Now we have x takes the value 1. Yes, that is fine. 2 fine. 3 fine. But 4 is not fine. But we can say that truth value is 0 when x is 4. Now similarly, whatever the value is there. So now in this case, these kind of statements where x are involved, it is called as open statements. Okay, and also the variables involved in this, like suppose the x which can take the value, are called as free variables. Now this x should take the value from the universe. X should take value from the universe u, which we were discussing above. Now if I take this case, x plus 3 is equal to 6. Now x should take a value from real numbers. Similarly, this x square should also take the value from real numbers. So now in this case, R is the universe, right? In this case, R is the universe. But now when I'm saying this, x will take the value from the universe. So this result is not true for all the values of x. It will be true only for when x will take a value 3. Right? In that case, what we can say is there exists some value x that belongs to the universe for which p of x, like, okay, now p of x is like these open statements are indicated with the help of the variables. Like now I can indicate this is q of x. See, earlier the variable was not associated with the propositions, but here I'm adding this variable. So in this case, like this 3. So that means there exists some value x in the universe for which p of x is true. But this is not true for all the values of x. That means for all will be represented by this. For all x that belongs to the universe, p of x is false. But this will be true because this will include the value 5. Now, if I substitute x takes the value from the universe, if it takes the value 5, then it will become a false statement, right? So, if we associate some quantity, if you associate some quantity with the open statement, then it becomes the quantifiers. See, here I am associating there exists. That means there exists some value in the universe. Here I am saying that for all the values in the universe, right? This is what the difference is. Okay, like now coming to how this will be helpful is in the representation. In the previous examples, we have taken only the particular cases, but here I am generalizing to the entire universe. Now, these kind of symbols, when they are presented to the computer, what discussion that will be, what decision that will take will be decided by the rules of inference. So rules of inference may play a major role in this cases. So by using this, I will you can continue the discussion on the artificial intelligence, how this can be used to represent the knowledge, and the computer can take a decision based on this statement. So in this session, what we have seen is how the statements can be represented by using the symbols, and how we can do the operations on these symbols and arrive at a decision by using some sort of the laws, which are defined by the like various mathematicians. So this representation of the knowledge, we can give it to the computer, and the computer can define or take a decision based on these arguments. Okay, so this is how we can develop an artificial intelligence. This is the knowledge representation to the computer on which the computer can take the decision. Like now, if you want to build some artificial intelligence based on this, then you have to give this statements to the computer. So the computer will arrive at a decision, okay, what you have given is valid or invalid. But how it takes based on some of the laws and then the logic. So these two are important. This is how the computer will take a decision in this. Okay, so now I will stop the session over here. So if you have any doubt, please do ask me. So or if you have any doubt in this, please do ask.
If you have any queries from Dr. Pavan, you can just ask now.
I will share the scribe notes of this talk. You can just use it, and also if I will send some material related to that. That you can take it from Chandramodi sir, and you can use it for reading further on this.
Sir, it's not regarding the PPT. I want to know how you wrote in the PPT slides, sir.
I didn't get it.
So how did you
writing it?
About near about 1600 students are there.
No, the query is how you are able to write it so easily in the PPT slide.
No, that is using a pen. That is using a touchscreen pad. Is there? Small pad.
You can show that by switching on your video for a while.
Okay, sir. Thank you.
Can you see this pen over here? I can just use this pen, and then using this I can write. Like there is a small pad which can be used. There is like this kind of a pad is there on which I can write so that you can see on the screen.
Is it a graphic tablet?
No, it's not a graphic tablet. It's just not having any display. It is a Vacom. The company name is Vacom or something. Yes.
Yes, sir. Thank you, sir.
Ma'am, there are these tablets available online on Amazon and Flipkart. They are called as write pads. So you can use that directly, attach it with your laptop. And when you write on that write pad, you can share that screen there. So that's possible. And whatever sir had written, you can convert it to a PDF and also send it in WhatsApp or email or anything. That can be done using these.
Yeah.
I think there are no queries for you, Pavan. It's only appreciations.
So, like, if you have any doubt, just try to see if you can use it. So, I just wanted you to have some idea of how about these things will work. So, you can continue your discussion taking advanced courses on artificial intelligence, and then like enrich your knowledge. And maybe someday you can explain me what exactly this is in a more sophisticated manner to your children also, so that they can also do well in their fields. Right? So, any doubt, please let me know.
So there is no doubt, and says as of now the things are very clear.
Okay, maybe in future you may get the doubt.
Yes, yes. Once they go back and
Sir,
see the people.
it's very easy to understand when it's coming to numbers. Only when it is coming to logical statements, that time we have to really correlate.
So, how about the participants, sir? Majority are from which place? Like they're based on?
From all over India, sir, from Tamil Nadu, from everything.
No, just representation wise, like just I wanted to know, like which.
Actually, my name is Radha. I'm from Chennai Computer Science. I'm taking computer science for 11 and 12. So from Chennai. The session was very good.
Sir, I'm Sharda from Bangalore, mathematics.
Sir, I am from Pune, Maharashtra. Sir, I am from Madhya Pradesh.
Oh, nice.
I'm Meena Verma. I'm from Pune.
Oh, nice.
So I'm Deepa from Abu Dhabi, United Arab Emirates.
Oh, maybe you are the farthest participant.
Delhi.
Oh, nice.
Sir, I am from Trivandrum.
Sir, I am from Bhopal. I am Saurabh Bharti, sir. 18 inches, computer science, sir. My background is computer science. But really, sir, your session is really informative, sir. I like math, sir.
Oh, nice. So I suggest you to like read into some of the advanced books and get into working in this area. That will be definitely helpful.
Yes, sir. Thank you very much, sir.
So it was a nice experience. Like, hope to see you in person sometime in near future. Like, I may not recognize you, but don't mind that part. So if you happen to see me, or if you happen to come to Dharwad sometime, please do visit our institute. You can say take my email ID from our institute website, and we will be happy to see you.
Majority around 30 to 40 from Tamil Nadu, Pavan, and around 15 are from Gujarat, and another 20 plus from Delhi, and there are 2 from Nagaland also, 1 from Meghalaya. There is so it was distributed throughout the country.
And yeah, few are participated from UAE also. That is very good. In fact,
Yeah.
or from ICT, I can say. So So my
Yes.
email ID is just dropping my email ID in the chat box, and also you can. I have just dropped my email ID, so you can use it. Spare some time, like within 1 minute. I'll just share another link as well. So that was my email ID, and this is my personal website. Also, you can visit our institute email ID at this address.
So, since there are no queries and it's only the
Sir,
series.
please contact number also, sir. Your contact number.
It's there on my webpage. You can just check.
Thank you.
So once again, I really thank Dr. Pavan Kumar, who is a very good friend of mine. More than a friend, he is to me. We had an association from in IIT for more than 4-5 years, I think. Thank you, Pavan, once again for a very nice and informative session. Thank you very much.
Thank you, sir, for giving an opportunity to talk with all the teachers who are really shaping and doing very hard work in shaping.
All our inputs are their outputs.
Yeah.
They are shaping and sending us to us.
Yeah.
So we need to be really thankful to them for sending a good set of children to the higher good institutes.
So it was really wonderful, and thank you for giving an opportunity. Also, like if the participants have any doubt, even you can contact Chandramoli sir. He's also an expert in machine learning and artificial intelligence, and he can help out with most of the things like queries you have or your students have. And also, it was a very good learning experience for me also when I was a PhD student at Indian Institute of Technology. It was a really nice experience interacting with him and learning so many things. So, like, if you get any session to attend, like, if you get the chance to attend any of his session, don't miss it. You can have a good learning experience from that as well. Thank you, sir, and also thank you for all the participants for your patient listening. Thank you. I hope the session was useful to.
Yeah, and
Thank you.
send that scribe notes to me so that I can share with all the people.
Thank you. Yeah, thank you all.
And we'll break for lunch now, and we'll get back sharply at 2 o'clock to have another nice, interesting session on emotional artificial intelligence. Till then, take care.
Thank you. Thank you, sir.
Thank you, Pawan.
Thank you, sir.
Nice session.
Thank you, sir.